So hello everyone. If you have any questions, feel free to ask and we'll try to get these. I'll try to have time at the end of this presentation. The purpose of the presentation that's the purpose, but the level of presentation is tended to stay rather high. I do go into some low level toward the end, have a little bit more for the developer community that may be on, but for the most of it, it is theory based. So our agenda is quite long for this next 30 minutes, somewhat. So first, to do a quick introduction of who GlobalPlatform is, go into some IoT security use cases, introduction to what is called the trusted execution environment, and I'll get to that much better later. Overview of a trusted application manager. And then finally, do a question and answer, depending on how much time we have left. So first, a quick introduction of who GlobalPlatform is. We are a standards organization, over 120 members. We divide into three main domains. The first one being card security, which is secure element. We also do device specifications for a trusted execution environment, or TEE, as well as other device enhancements, over-the-air management, access control, and so forth. And then we do system specs, or cloud specs, if you want to call them that, for managing a secure element, for service providers that provide services to their customers, for control and authority, which is a trusted third party in the chain, and trusted service managers, which are mostly aggregators between a service provider and a secure element issuer. So I'll go into the card and device. The systems is kind of along the line of a trusted service manager or trusted application manager, and we'll see those later in the presentation. So just a screenshot quickly of our membership. The top tier here, the top third of the screen, is our full members. The middle is our what's called the participating members that have a lot to do with our specs as well. And the lower level, or the bottom level, is our observer level members. So give you an idea that we have from device manufacturers to the chip makers to the infrastructure providers to the service providers like MasterCard, chip manufacturers, like I said, NXP, Qualcomm, so forth. A good variety of industries or industry companies represented. So, brief history. We started in 1999, and our whole purpose was to digitize stuff that was going on to cards, credit cards, ID cards, and so forth. So for the first roughly 7 years, we developed the specifications for the chip card technology. For those of you that have the cards now that have the chips embedded in them, the majority of those chips are running our specifications on how to manage those applications on that chip. Roughly 2007, the advent of NFC, near field communications, was put into mobile devices, and we then started our focus on how to put the secure cards, the secure chips, into mobile devices. For those of you that use Apple Pay, you are using that technology. Android Pay, Samsung Pay, they use it in parts and pieces, and I'll get into that in a few moments. And then roughly last year onward, we see this now going into the Internet of Things, where we have a majority of our new internet devices are no longer mobile phones or PCs, but they're different kind of devices that come out in the market. And the question is how do we secure these things? How do we make them where there is a way that we can trust information that is being shared, being sent to these systems? The idea is that if we have a internet gateway in our home, how do we make sure that internet gateway is not being compromised by some third party getting access to our own private information? So our specifications, we're an open standards body. The standards can be downloaded from our website free of charge. we offer interoperability, flexibility, a multi-application and type environment, and also the security. So our basics is that we are a security-based organization, and that's our specs are based around that. How to make sure there is the compromise between security and usability. And we strive to make it as usable as possible while maintaining the security that people need. Our specifications are not a all or nothing proposition. As I mentioned earlier, Android Pay, Samsung Pay, both use parts of our specification. Apple Pay, while it uses the card spec a lot, their secure enclave uses other parts and pieces of our specifications as well. So we see a lot of specifications in different areas. So the question is kind of how successful have we been? Well, between 2013 2015, we estimate that there's been approximately 17 billion of the smart cards, of the secure elements. Remember, the secure element it's a chip that is very much tamper resistant. It is made for maintaining credentials at the highest security possible on a form factor that can be easily used. So looking at now, how is that going to be used into, or how it's going to be deployed into IoT? So let's get into some IoT use cases and try to understand a little bit more of what is the security needs for IoT. If you look in the media today, most of the IoT is around how security is non-existent. Most of these articles came from the first half or the first quarter of this year. If you look today, you'll see a lot more coming out. Stuff like a person invading or a hacker, I should say, hacking into a home network and taking over a baby monitor, or cars being shut down remotely, or HVAC systems being compromised and the hackers jumping into other systems in the network. So these are very real and very publicized attacks. We just had the attack last week or 2 weeks ago of parts of the internet being taken down, and they attributed that to hackers coming through Internet of Things systems. So our membership knows that there is a lot of potential in IoT. So if you notice, we have AMD, Huawei, ARM, NXP, Gemalto, and so forth listed here in these different articles where they are looking at how they can implement IoT and secure those Internet of Things as well. So making sure that there is some kind of security in the background for your devices. So what kind of security requirements are we looking at? Well, in order to communicate with a cloud to a system level in the background, we need to make sure the communication is encrypted. Or if it's from device to device, that there's some kind of way for that device to be authenticated, identified, that it just doesn't allow any device attached to it. If it's coming through a gateway, to make sure that that gateway has some kind of way to identify who is coming through for identification purposes, access control, the privacy issues. So there's many different aspects of in the IoT landscape, what is required for a successful network to operate, and at the same time to protect itself from intruders, from attacks. One world example we can point to, there's an organization called BSI. It's the security organization of Germany. In other words, they dictate what is required for the security standards inside of Germany. They also, the German government came out and said that every home needs to have a smart meter to be able to make sure that the electricity being used by the home is first off being monitored, but also not going out of whack. In other words, they want to make sure that every household is using electricity wisely. One of the issues they ran into, however, is when they stream the meter data over their network, they introduced what's called a side channel attack. What that basically means is that you could monitor the power being used by a home, and based on that monitor usage, you could tell what they were doing, and down to the fact that you could sometimes easily determine what they're watching on TV, the way that the power is fluctuating. The way they got around this, or what they said to do, was to put a secure element into their gateway. Basically, the home would then report to the gateway the secure element. With the secure element, that secure element would gather the data and then publish it up to their meter network, so that you could have your information about the home usage, but in a abstract manner and not a direct streaming manner. So one example of an IoT in a smart city setting, in where the security of a secure element is being used to make sure the privacy of the home is still maintained. Another example is one of our member companies, NXP. This is a diagram of what they see for a smart car. All the red circles are secure elements where they're using to control communications into and outside the car. Well, except for the one on the bottom left, that is a data recorder. They use a secure element to make sure that the data that's being written is not able to be compromised. But if you notice that any communication outside the vehicle is going through some type of security channel, that way that a hacker is not able to go through the network without appropriately go through one of these network nodes without properly identifying who they are. So let's go into the secure element a little bit more on what it offers. So the secure element by itself is probably the best identified as a state-of-the-art root of trust. It has its own keys. It's hardware embedded with the keys. It has a cost-effective crypto processor, meaning that it can do the proper crypto algorithms pretty effectively. Hardware-based in most regards. It has also been certified and reliable. We go through, our secure element has to go through several types of testing before it can be called a secure element, whether it be common criteria, or FIPS, or EMVCO, or others out there. It has a unique identification. Basically, every secure element has its own unique identifier. It's a reliable crypto environment. So like I said before, it has its own crypto processor. More than that, in order to become a certified secure element, it has to go through a crypto testing. So it has its crypto engine protected in many different ways. Obfuscation is one of those, in which a side channel attack if it detects a side channel attack, it will shut itself down. Again, a side channel attack is somebody coming in, monitoring either the way the power is being used by the processor or so forth. And then we have also the remote administration. So one of our biggest advantages over any other standards out there is that we allow for for remote administration of that chip. So part of our specifications in the cloud type specifications is how to actually manage that environment on behalf of a service provider. And it's two main modes. You have the services that it's being directed toward the device, as what services does it have for the device itself that it can provide, like secure boot or storage of keys and so forth. And then you have the secure services of the application. So processing different systems, or allowing for the electric usage to be able to be shown in a abstract manner. So that's the coverage of the secure element. A secure element, before I go much farther, a secure element uses, in most cases, 99% of the time, uses a Java card type backend. For those of you that know Java card programming, you know it's not a easily programmable area. It's on purpose. The trusted diffusion environment, however, is a different way of doing the security. Not quite as secure as secure as a secure element, but it does have its own attributes. So let's go into that for a few minutes. So trusted execution environment is a secure area on its own processor. So for those of you that might have heard the term trust zone, ARM released or has a system called Trust Zone, in which it on a main processor, Qualcomm or whoever may be, NVIDIA, they switch from a normal processing to a secure processing, and it's a hard switch, meaning that they're either in a regular processing mode or they're in a secure processing mode, and we'll get into that a little bit later. The main issue is, or the main advantage is that it's able to isolate the execution from a rich environment application and a trusted application. So the sensitive data, the other systems that are stored in the TEE is isolated from the rich environment. Doesn't mean there's no interaction. We'll show that in a few minutes, but it means that the communications is very trusted back and forth. Today, how is it being used? Have it being used so far in Android. So if Android 6 requires a TEE for biometric readers, as I mentioned before, the specs do not have to be as all or nothing. So we have a trusted UI specification, and Android 6 requires a trusted UI, trusted user interface, to be used when you do some kind of biometric authentication on the device. GlobalPlatform and FIDO is faster than the online, have a memorandum of understanding in which we are working on certification between a GlobalPlatform enabled identifier to be used in a FIDO system. And we also have working with an organization called 1M2M. 1M2M recognizes the GlobalPlatform TEE as their level 2 protection when they're talking between two IoT type devices. So one example here of a possible hack is the idea of Waze. For those of you who live in California, Waze is kind of taken over out there as far as the way it works. It's starting to propagate itself in other parts of the country as well. The idea is that it's a crowdsourcing type of traffic system, so that as you use the Waze app, it understands, or it can determine whether you're going 60 or 6. So it knows whether you're going full speed or you're stuck on the road. The issue is that a hacker can fool it by basically saying that they're only going 6 when they're actually going 60. And they report the bogus information to Waze, and Waze then redirects other traffic around a false traffic jam or false accident. So in a rich execution environment that normal phone uses or device uses, you have the idea of its rich OS running on some kind of hardware platform like an Android or Apple or whatever it may be, and the applications running. Your many applications that you download from the App Store and have them running. A hacker wants to get into those apps, and when he does, his first thing he does is puts a rootkit into the system that basically takes over the OS, or has the ability to get into the OS of the device. And from there, they can control different services like the GPS, like the communications, like sending SMSs on your behalf when you don't want to, those kind of things. So what the trusted execution environment does is, first off, it boots from the hardware itself. Our specifications state that it must boot first before the rich OS boots, so that it is booted out of a hardware key set that is never seen by the rich OS, and it boots into its own trusted environment that the rich OS has no control over. It has a trusted core framework that allows for it to operate with applications. trusted drivers to talk to different kind of hardware systems, and a trusted communications agent that allows your communications with the rich OS. There are some published APIs that then also allow for the applications to communicate with the trusted framework. And we have our own APIs inside of the rich OS that allow for the applications rich OS to securely communicate to the trusted execution environment. And then you have the trusted apps that are running in the trusted execution environment that handle the activities that you need to handle. So when a hacker comes in and puts his code into the rich OS, when he tries to move it over to the TEE, we don't trust it and we throw it away. To give a little bit more in-depth example of how this actually works. So when we have an application that's running, client application running in a rich OS that wants to communicate something to a trusted execution environment, there is the idea of shared memory. By default, your application in the TEE does not trust anything in a shared memory. It always checks to make sure that it is current, it is correct. There is nothing that is that's like a rollback or whatever type of attack being happening. But in essence, a message will be generated by the client application. It sends it through TEE protocols to the client API. The client API communicates with the communications agent that then goes through the messaging part of the hardware, and a switch is made. Remember that the processor itself switches from real-time operations to trusted operations, and it does that hardware switch as that message is passed. So it's now in the TE communication agent. It looks at it and see what it needs to go to. Goes to the trusted core API, internal core API, to handle any messages that it needs that needs to be done, and finally to the trusted application. The trusted application itself can also generate its own message to another trusted application through the API, get a response back, and with that response, then send its own response back through the system, back through the core API, the communications agent, messaging system, and back up to the application to be processed. So that we have specifications that are free to download that describe this environment, the architecture, the device access, or was a client API itself, the internal core API. We also have several other APIs there, secure element APIs that I was talking about earlier. The secure element is there as a very trusted system. The TEE is in memory itself. It is not quite as trusted. In other words, it's not as tamper resistant as a secure element. So we have an API that you can use the secure element to actually store very, very sensitive information. Even more sensitive, you want to leave it in a TEE. We also have a sockets API that allows you communications, sockets or internet type communications from a TEE out. Trusted user interface, as I mentioned before, being used by Android 6 already. And also a TA or trusted application debug specification. The bug specification is there to allow users to be able to debug, or actually developers to be able to debug their applications as they're developing them. There is the protection profile that describes how a TEE is protected. What does it do to protect itself? And then the internal configuration test suite, or I should say the initial configuration test suite, in which we have several compliant TEEs already in the market. You can go to our website under compliance and see those devices or see those implementations now. So I'm going to talk a little bit more in depth about the TEE access for the client API and the internal core API. So when we want to have a client, in other words, your application sitting in a rich OS to talk to the TEE on that particular application, it first has to open up a context with the TEE, basically saying, "Hey, I want to talk to you." You notice there's a if result is not equal success, as in there's no TEE in device, then you can't do anything, and you get some kind of result that is, sorry, you can't talk to me right now, or the TEE may be shut down for whatever reason. Once the context is set, you then open a session with a particular application. So you define which application you want to talk to through UUID, universal or unique universal ID. Every application is defined by the UUID, and you then can exchange information through a command operation, some kind of a TEC invoke command. So look at this a little bit more. The trusted application has itself a TA interface. In other words, what does it need to communicate with the applications on the rich environment? So they are the entry point. Don't do that. The create entry point, which then constructs a new operation to be done. Destroy entry point, which basically tears down that application constructor. The open session, entry point, and close session, and invoke command. So these are items that are needed to be implemented in a trusted application in order for it to be able to receive and process commands on behalf of our client. So you can also have different configurations for the trusted application, whether it has a single instance, as in single-threaded, or if it's a multi-session or multi-threaded type of system. In other words, set up multiple instances of itself to be able to support multiple sessions. Keep alive, as in, what's going to happen when the TE shuts down? Does it still remain active? In other words, when the TE comes back up, is it still there? The data size, the stack size, what version it is, and what the description may be. So the TA description is basically how you describe your trusted application. Also, it can get information about where it is, as in the client identity. Ask the client, who are you? So the client application, that is. Ask the device for its identity. Ask the TE for its version. All of these can be getting through a string, a Boolean, or what have you, for different types of data types to be received. And TAs also can commit suicide. So anytime that any information is sent to the TA that does not seem to be correct, as in the TA doesn't like it, or TA is asked to do something that it thinks is questionable, it may commit suicide, as in throwing a panic. And a panic simply says the trusted application shuts down and destroys all the resources there. So if there's any chance that I am being attempted to be compromised, my TA will panic and shut itself down. Trusted storage allows for the use of or allows for the storage of keys and other data objects. There's a persistent storage that can be accessed by or can be accessed by the TA at continual times. There's also the transient, which is basically just a set up and torn down transient type, whereas it's just for one-time use. And there's multiple APIs for managing persistent and transient objects. And due to the time, I'm not going to get into those very much. There's also more parts of the internal core API I'm not going to go into on this, so we're running out of time, and I want to allow enough time for questions. So the encrypted or the crypto API is part of the internal core API that allows for cryptography functions. Time API to be able to get what time is in a system or in a TA, and arithmetic API to allow for your own arithmetic functions. Even if you want to make your own crypto system, you can use the arithmetic APIs. And there's a limit basically on how much, based on how big the variables can be based on the implementation. You can get that by that last property there. So let me switch gears and go into the Trusted Application Manager. So the Trusted Application Manager is a relatively new topic. We've had the specification released recently, and it's an overview of what a Trusted Application is. Trusted Application Manager is it's a system that provides a scalable and remote means to managing the trusted execution environment, a security domain, and I'll talk about that in a second, and a trusted application itself. So they enforce the security policies that are either set up by the trusted application providers, the TE issuers or implementers. They ensure the security of those systems, and they also deal with everything in a confidential way. Now, a security domain, go back to in a moment, go back to a little bit. A security domain is a system or an application, I should say, that allows for certain processing on the TE. So it allows for the basically for a trusted application to be able to handle the security mechanisms or be able to have different states, whether it's active or deactive, or inactive, I should say. So the security domain is a way of maintaining the state and doing a crypto processing for a trusted application. So look at how a TAM operates. Note that this is there's all different kind of ways that this can actually operate. So don't think this is the only way. It's just an example. That little stone wall in the device is meant to represent the trusted execution environment. So a service provider will publish their application on an app store, and it will have inside of it also the TA, the trusted application. A user can download that application into their environment, so into their Android device. When they open the application then goes back to the service provider and says, hey, I've got a TA portion on me that needs to be installed. After the service provider processes that, yes, this is a valid request, it sends back a certificate to the application and to the device saying, here's a certificate for you to install your app. The certificate is then taken by the TA and installs into the TE. So now I have an application or TA trusted application installed in the TE. Now, TA personalization is basically what information do I need in order to personalize that TA for the application. If it's a banking application, it may have my credit card information. If it's a key for the home, it may have the information on my door lock, and so forth. So give a shout out to one of our members is Trustonic. So they have a trusted application manager, and their trusted application manager has a way to download to a Android device. Now, when you download to an Android device, they determine whether that device has a trusted execution environment on it already. If it does, they're able to then download the appropriate app with the appropriate TE or trusted application. If not, then they have their own encryption systems to encrypt the software best means possible. So it's not a TE, but it's another way of trying to protect your information. So with that, now time for the question and answer. I'm going to switch back to the other mode so I can see your questions. So the question is, do you need to be a member to use our APIs? No. So there is a section on our website for IPR. GlobalPlatform itself allows for the download of our specifications free of charge. We need to check on the IPR disclosures. If there's any IPRs and the specifications you download, the owner of that IPR may request a license. But other than that, you're free to download and implement to your heart's desire. So the question is about more along the lines of a market or a wide application and market enabler. So I concentrate on the TEE in this presentation on a trust application inside of an Android environment. However, our biggest pickup is in the IoT area. We just had a hackathon 2 weeks ago in which we had a Raspberry Pi running a Linux system with a TEE inside the Linux system. And the winners were able to put their applications, a crypto application, a IoT access control application, a password generator, all in TEE and run those on a Raspberry Pi. And most of those for the, especially for the second runner-up, it was strictly for an IoT type device. In other words, their idea was rolling. It's called rolling IDs. So they would change the ID of a device every second or so. So a GPS locator or some other kind of tracker could not be tracked by hackers. Interesting idea, and they secured that mechanism, that ID inside the TEE. We also see it being picked up by DVRs, DVR players to do premium content. We see it being picked up in many other areas as well. So the secure element is being used already in many areas for some devices, but we see TEE also being used in in devices that require a little more user interaction. So by the way, if you want to have more information about the hackathon we just did, you can go to tehackathon.org. I think I spelled it right. And if you look for VentureBeat under Global Platform, you'll see also a write-up on the hackathon we just did. Okay, so we're officially out of time. Don't think if there's no more questions, I appreciate everybody's joining us on the call. And I know this to be recorded, available for use later. At the very beginning of this, I put out my email address. So if you want to contact me directly through email, you're welcome to. With that, I'll go and close it out. Thank you, and bye-bye.